Hello and welcome to this video continuing with special right triangles. We are going to be talking mostly about isosceles right triangles, but we're going to start with a little review of 30, 60, 90 triangles with some unique situations that you could encounter with these sorts of problems. So 5 and 6 we actually talked a little bit about in our last video, but we're going to run through them really quickly again just to make sure we're all on the same page. So for number 5, we are basically going to be filling in our missing angle first, so our 30 degrees, and then write in our pattern on each side for these types of triangles. Our hypotenuse is always going to be 2a, across from 30 degrees is always a, and across from 60 degrees is always going to be a times the square root of 3. Now, if we have this set up, we can then use what our given side length was in order to find the rest of our sides. If I know that 2a is 26 root 3, you can kind of think of it as like we basically have 26 of these root 3s, 26 of them. So half of that would be 13 of them. So our a would then have to be 13 root 3, which would be half as many as 26 root 3s, which is 2a. Now, if I have a root 3, I'm going to do 13 root 3 times one more root 3. Whenever you have a square root times a square root like this, where they're both the same number underneath, you get rid of the square roots and it just equals what's underneath, meaning that we just have 13 times 3 equal to 39 for that side. And so we have all three of our sides of this triangle. And this is kind of a level 2 example. And we're going to do another one in a second with number 6. But generally speaking, in the future, remember that if we were talking about a 60-degree side, that would be this 39. And then the 90-degree side is the hypotenuse. 30-degree side is across from it right here. Moving to number 6, in this case, now we have a 30-degree angle across from 11 root 3. So in our pattern, that would be our A. That means that our 60-degree side is up here, and that is A root 3. And then our hypotenuse is 2A. So that means that we can use our A as 11 root 3. We can double that to get 22 root 3, double the amount of root 3's. And then we're just doing 11 root 3 times one more root 3, which is actually going to end up being 11 times 3 and getting us an answer of 33. The steps, no matter what, are going to stay the same in that you are figuring, well, what angle are you missing? Write that in, write in the pattern, that's step 2, and then determine what each side is using that pattern. And you can see that's what happened in both 5 and 6. The next two problems below are different. If you look at the given information, we see that across from 60 degrees is the number 12. Usually it has a root 3 in it in most problems. So let's start by writing in our angles and our pattern. So the 12 is supposed to be A root 3. This is supposed to be 2A, the hypotenuse side, and then across from 30 degrees would just be A. And that is a little different than what we have already seen before. So if I know that I have at the bottom here 12 is equal to A root 3, in order to get A by itself, I have to divide by root 3. So I would do 12 over root 3, and then A root 3 over root 3. So you can see right there that I have a, focus our camera. So we have a root 3's we can divide out. So our answer for A is 12 over root 3. So that doesn't exactly look how you want it to look. Root 3 is an irrational number. It's a generally accepted convention in all of math that you don't want to divide or have a fraction with the denominator being irrational. And that's what root 3 is. So we want to do something called rationalizing. So if I want to rationalize, and this we may want to zoom in a little bit more here. So now that we've zoomed in a little bit, we're going to take the 12 over root 3, and I'm going to multiply it by root 3 over root 3, like so. Now, if you multiply by root 3 over root 3, that's just multiplying by 1, really. So we're not changing anything, but we will have 12 times root 3 on the top of our fraction. And then you can see at the bottom, we have root 3 times another root 3. We talked about that earlier as being equal to just 3. And if we have 12 root 3 divided by 3, well, I can just do 12 divided by 3 and figure out that my answer for A is just 4 root 3 equals A. So that right there, we just solve for A. That means that my A side up here is that answer I just got, 4 root 3, the rationalized version of it. And I can double 4 root 3 easily to get my hypotenuse as 8 root 3. Now, you guys should try to pause the video here to see if you can solve for the two missing sides of our triangle on the right. Like before, we want to write in our missing angle and our pattern on all three sides. So I've done that right there. So we want to then do exactly what we were doing before. We want to figure out what A is and then rationalize it. So I would have 10 over root 3 and then a root 3 over root 3, allowing me to get rid of the root 3's on the right. So my answer for A is 10 divided by root 3. But we don't want that square root on the bottom. So I'm going to multiply again by the same square root as I have on the bottom. And in this particular problem with 30, 60, 90 triangles, it's always going to be a root 3. But in our next topic, it's going to be a different number. So if I multiply across the top, I got 10 root 3. Multiply across the bottom, I get 3. So that's my A. A is equal to 10 root 3 divided by 3. No way to simplify that anymore. So if I wanted to double this, remember when you're doubling a fraction in general, you just double the numerator, and that's going to cause the fraction to double. For example, doubling 3 over 4 would be 6 over 4. That means that our 2A is going to be 20 root 3 over 3. And that finishes some level 2 and then level 3 problems of 30, 60, 90 triangles. And you know that they're going to be like this if you have that root 3 in a different place than it usually is across from 60 degrees, or if you have a side across from 60 degrees that is just an integer and doesn't have a square root at all. So now we're ready to move on to isosceles right triangles. And we're going to move into our next page here of our notes. So in this example here, we have two triangles that we'll kind of label as triangle 1 and then triangle 2. And we may want to zoom in a little bit on these, like so. So now that we have these zoomed in, let's look at triangle 1 first. So if I'm going to try to figure out what the sides that are missing here are, we would have X and then Y as our goals here. You can see that the 6 has a double side marking, and then this has a double side marking. If you think back to our geometry chapters in the past, that means that both sides are going to be equal to 6. So we know X is equal to 6. Now we have a right triangle with two sides, so we can use Pythagorean theorem. So that means we would have 6 squared plus 6 squared is going to be equal to y squared. Now, if I know that this is true, well, I can do 6 squared plus 6 squared, which would be 36 plus 36, and that answer is 72 equal to y squared. So the square root of 72 would equal to y. But just like every other topic we've done this year, we want to simplify square roots whenever we have them, if possible. So if I do our tree method here, we have 12 times 6. 6 is 3 and 2. 12 is 4 and 3. And then 2 and 2. So our tree is done. We have 3 2s and 2 3s. So we want to put a little circle around a pair of 3s. And then we will put a circle around a pair of 2s. So we would have on the outside 3 times 2 equals 6. And then on the inside, we just have this 1, 2 left over right there, so that our answer would be 6 root 2. Okay. So moving on to our next problem, we're going to see if this kind of seems like the same pattern is happening. So if I know that I have a 45-degree angle and this is 90 degrees, that means that my other missing angle in triangle 2 is also 45 degrees. Well, if we have a right triangle with two angles that are the same, whenever you have two angles of a triangle that are the same, that means it's an isosceles triangle. So x and y are really going to end up being the same number. So I can really just label them both as x. And I know that 4 square root of 2 is going to be my hypotenuse side already. So for this triangle on the right, we can write that as x squared plus x squared equals 4 root 2 squared. And that's just Pythagorean theorem, exactly as we did it before. X squared plus x squared is 2x squared. And 4 root 2 times 4 root 2, if you do that in your calculator, that's basically, we can just write it right about here, 4 times the square root of 2 times 4 times the square root of 2. And we could even check this on a calculator. It's going to end up being basically 4 times 4 is 16. And square root of 2 times square root of 2 is 2. And then 16 times 2 is 32. But if you wanted to prove it to ourselves that that is the answer, 4 square root of 2 times 4 square root of 2, we get 32 as an answer, double checking our work. So in this problem, we have 2x squared equals 32, and then divide by 2, we get x squared is equal to 16, and that means that x is going to be equal to 4 for the sides of this triangle. So we have a 4 and a 4. So you're looking at these triangles, it might seem that we have a pattern going on. We have both of them are isosceles triangles, two sides are the same. Both of them are right triangles. And then also the sides here are both 6. The hypotenuse is 6 root 2. The 4 and 4 are our legs, and then 4 root 2. And that brings us to the pattern of this type of triangle. So we're going to call this two different things. One way to call it is isosceles right triangle. Or we could also call it a 45-45-90 triangle. But isosceles right triangle has a nicer ring to it. So we'll call it that. And then the pattern that we are going to be using for these types of triangles are going to be basically x, and then x times the square root of 2. And we could check to see if that works. X squared plus x squared would have to equal x root 2 squared. And we've kind of already proved that by working backwards up here. And this is the pattern that you would follow in order to solve for the missing sides if you knew you had an isosceles right triangle. And we also know that these two angles are the same in addition to the two sides being the same. And these are always going to be 45-45. So we can write those in as well. So this would be an important pattern to write down in our notes and have as our jumping off point for this example here. Now that we've done that, we're going to work through about 6 examples of finding all the sides of an isosceles right triangle. So we'll move on from these notes now. Okay. So we're going to kind of work through these examples, kind of doing the same thing we've been doing lately with these. And we'll refocus our camera and get to work. So with all of these, you can see we have the kind of double markings here. So this is kind of similar to what we were doing before. We kind of actually done this problem already. So we'll just skip number 1. We kind of already did that already. In number 2, we know that we have angles that are the same. That means we have an isosceles triangle. So it would be a 5 here. Since these are both x, y should be x root 2. That means that our hypotenuse is going to be 5 root 2. Pretty straightforward stuff right there, even easier than a 30, 60, 90 triangle. Moving to numbers 3 and 4, this is kind of the same idea here. So number 4, for instance, we know we have 8 and 8, so we have 2 sides that are the same. Those are both supposed to be just a, if you want to use different letters, since we already have x in this problem. This is supposed to be a root 2. If 8 is a, then obviously a root 2 would have to make this hypotenuse side 8 root 2. Now 4 root 2, and so with this one, with x and y, it doesn't show that they're the same, but they are in fact the same. So we do have 45 and 45 degrees for our angles. And then we would know that 4 root 2 is supposed to be a root 2, and both of these would end up being equal to a. So if you kind of compare these two right here, 4 root 2 and a root 2 means that 4 would be equal to a, and 4 would be the length of these two sides of this triangle. So we have level 1 is really straightforward. You really have just two sides are the same. The hypotenuse is always that same number times the square root of 2. And it's a pretty straightforward pattern to follow along with. What will become a little bit harder is if we have problems like 5 and 6 right here that we're looking at now, where you can see that if we write in our pattern and our angles on both of these, for instance, this 8 is supposed to be a root 2, and these two sides are both supposed to be a. Now, if I have that much, I'm basically going to use the rationalizing step eventually from what I was looking at in 30, 60, 90 triangles. So if I divide both sides by root 2, I would have a 8 over root 2, and then a root 2 over root 2. And then I can divide out the root 2's. So I just have a divided by the square root of 2. But now I got to rationalize this like I did in the earlier problems. So I'd be multiplying by the square root of 2 divided by the square root of 2. And that would give me the answer that I am looking for in the problem. So I'd multiply across the top and get 8 root 2. And then root 2 times itself would be 2. And then 8 divided by 2 would give me just 4 root 2. So that 4 root 2 would end up being my a value after I've rationalized this. And that kind of looks a little strange that we have kind of basically it flipped around. But that is how these sorts of kind of level 2 sorts of problems would work. And finally, our last problem of this section is going to end up being number 6 here. So we have 45 and 45. So that we need to say that 10 is a root 2. So if we kind of use our last one as an example, we're going to end up with 10 divided by the square root of 2 as our a value. So if I want to find that out, I got to do 10 divided by the root 2. I got to rationalize that like last time. So I got to multiply by the square root of 2 on top and bottom. So I would have 10 root 2 over 2. And that would just require me to divide 10 and 2 together to get that my a value is 5 times the square root of 2. And that would make my last side here and here my answers for the rest of this triangle. And that concludes the examples of isosceles right triangles, also known as special right triangles, and completes our video today. Thank you for watching this lesson video.